Good morning, everyone. So the next assignments that we have are homework 6 and homework 7. They're both pretty similar. For both of the assignments, you'll be building a parallel sorting, an implementation of a parallel sorting algorithm based on quicksort called sample sort. Now here's homework 6. Now you've got a description here of sample sort, step by step. This is the procedure that you will want to implement, is sample sort as described here. But separate from this description, I want to go ahead and walk through the motivation of sample sort and give some idea of how it's supposed to work. So sample sort is a parallel version of quicksort. And so to figure out why we would come up with sample sort, it's worth taking a little bit of a look at how we can parallelize something like a sorting algorithm. Now, the simplest sort of parallel sorting algorithm to explain is, well, a simple parallel sorting algorithm to explain is merge sort. Let me walk through that really quickly. So let's take some numbers. How about 3, 5, 22, 9, 35, 61, 2. And so the idea with merge sort is that we're going to take our list of numbers and we're just going to split it in half. So we have, what do we have here? We have 4 7 numbers. So we split it in half sort of unevenly. And now we have a left half and a right half. And with merge sort, what we're going to do is recursively merge sort both sides. So let me just go ahead and walk through and do that. So on the left side here, we'll split it in half. Then on the left side, we'll split it in half. And now we discover that 3 and 5 are arrays of length 1. An array of length 1 is sorted, so we're done with 3 and 5. We don't have to recurse anymore. What we're going to do then is we're going to merge those two together. And so we take the two sorted lists, merge them in such a way that we end up with maintaining the sorted property as we end up with a list of length 2. So we do that by figuring out which one comes first and putting it first. And then we have the rest of our list, 22, 9, 35, 61, 2. Now we can split here, and then we can merge. Then we split here, then we split here, then we merge. 35 comes before 61. I'll just go ahead and cheat and merge here because it's a length 1 thing that's already sorted. And then we would continue this to sort until we've merged everything back together and have a single list. Now, the splitting process with merge sort is basically 0 work. We don't have to look at the numbers at all. All we need to do is split the list in half until we end up with the size of 1. So we don't do any work on the way down, we do the work on the way back up. In order to parallelize merge sort, we can go ahead and say, so the splitting process is pretty inexpensive, but for the merging process, that's where we have to do the parallelization, or that's where the parallelization matters. That's where it's going to give us a speed up. The idea is the sort of split and merge at the first level of recursion is sequential. There's no way to take our list of, well, let me go ahead and do the rest of this merge just so that we have what the example is. So it comes out as 3, 5, 9, 22, and then 31, there's 35, 61, that merges with 2. And so when we go ahead to merge this back together, so the sequential split is free, but the sequential merge step where we're merging together 2 lists back into 1, that has to be done sequentially. There's no way to make that be multiple processes, because the operation is that we first compare the first 2 items in the array and pick one, and put it in the output list. Then we compare the first 2 items in the arrays and pick one and put it in the output list, and we repeat until the 2 input lists are empty. But if we tried to do it in parallel, we'd get into data races. But then once we're doing a split of 2 things, we can split 2 lists or 2 arrays in 2 processes, and the resulting join here, or the resulting merge, can also be done in 2 processes. We can merge our 4 arrays into 2 on 2 separate processor cores, and thus expect to get a factor of 2 parallel speedup on this step. And the total number of layers is the total number of levels of recursion that we have is log n, and the maximum parallelism that we can have is 1 plus 2 plus log n. Unfortunately, that means that the maximum parallel speedup that we can get is around log n as well. So if we want to sort a million items, log 2 of a million is 30. And so if we have 10 processor cores and we want to run it in 10 processes, we can probably get a speedup of around 10. We'll have to do that final merge sequentially, but then like 2/3 of the layers of recursion, we'll be able to use all 10 processor cores. So, I mean, we could do out the arithmetic. We would discover that 10 processor cores give us a theoretical speed up here of like 8 or something, but that's not terrible. We can do pretty well. But on the other hand, as this scales further, or sorry, as this scales less, as we go to less levels of recursion, we get basically no speed up. So merge sort parallelizes reasonably well, but it can't sort of scale indefinitely. What can scale indefinitely, and the reason for that is that we're stuck with this sort of sequential layer and the layer where we have only 2 processes that we can work with, etc. So let's take another look. Let's take a quick look at quicksort. So this is merge sort. So quicksort is sort of the opposite of merge sort, logically. We start with the same numbers, and the thing that we end up with is that we do the work on the way down. As we do the recursion, we're doing all of the sorting, and once we get to the bottom, once we're down to arrays of length 1, the entire process is done. There's no work to be done after returning from recursive calls to sort of stitch things back together. So we partition And so our partition is going to, we'll pick some item as our pivot. And just for the sake of simplicity, we'll take 9 as our pivot because it happens to be in the middle of the data. And then we move 22 over here, and we move 2 over here, and that has successfully partitioned our array so that we have the small numbers on the left, the big numbers on the right, and the pivot in the middle. Then we can go ahead and recurse on 352 and 356122. And eventually in our recursion, we get down to having sort of single array 2, 3, 5, 9, 22, 35, 61. So that's the bottom of our recursion, but at that point we have a sorted array. We just throw out our memory of where things were split, because with quicksort we can do an in-place sort. So by the time we get to the bottom of the recursion, we're just done. We stop, and there's not even anything to draw here. We just throw away the sort of vertical bars marking the splits. I mean, they're not vertical bars, they're like array indexes or something, but we can just throw them away. We don't need them once we've gotten down to the base case of the recursion, because at that point, all the work got done in the partitioning steps and we're sorted. Now, it looks like we have the same problem here that we had with merge sort, where this partitioning step has to be done sequentially, because we're picking our partition and then we're scanning through the array. And the normal way to implement this with sort of an array and doing it in place is that we're going to do swaps. If we find out that something is on the wrong side, we swap it with something that's on the correct side. If one side gets too big, we're going to swap it with the pivot. But sort of the straightforward way to do partitioning is sequential. But it turns out that parallelizing it can use a couple of tricks. So the first thing that we can observe here is that there's nothing magical about picking one pivot. We could do 2 pivots, or 5 pivots, or 10 pivots. And if we do that, the sort of basic process of partitioning doesn't really change. If you remember algorithms, and happen to get this example in algorithms, one of the examples that is pretty common in algorithms is what happens if we do quicksort with 2 pivots. Does it change any of the asymptotic complexity analysis? And the answer ends up being, at first it kind of looks like it might, but then it doesn't. Because as you increase the number of pivots, the sort of work of partitioning gets this like intermediate sorting step where you have to sort things into multiple buckets, and the like complexity that you save in having multiple pivots goes away in dealing with multiple pivots. But the other thing that we can do, and actually we could do this with just 1 pivot, is if we're willing to be sort of temporarily out of place, if we're willing to copy once. And yeah, that requires a little bit of extra space and might even increase the sort of conceptual cost of the algorithm by a factor of 2. But we can do the partitioning in parallel in up to number of pivots plus 1 processes. Once we've picked what the pivots are, then we can have any number of processes scan the array and pick off items from the input array that sort of go between any given 2 pivots. Now, there's a little bit of complexity in that each one of those processes then logically still needs to scan the whole array. And there's ways to work around that we're not going to deal with for this particular assignment. But we can do that array scan in parallel. And by doing that array scan in parallel, we get a... we don't actually get a speed up as far as asymptotic complexity goes. We're doing the same amount of work. In fact, we're doing slightly more work. Actually, we're doing more than slightly more work. We're doing p times more work in p processes, but we still get a experimental parallel speedup because on a multi-core CPU, every processor has its own cache hierarchy that don't share bandwidth, at least in the just sort of low-level caches. And multiple processors don't share memory bandwidth entirely equally. And so even if we don't do the optimizations to actually let us save work asymptotically, by doing this picking, we'll still get a parallel speedup. Now, there's one problem here. In order to get a good parallel speedup, we need to pick the right pivots. One of the problems with quicksort is that sometimes you pick a pivot, and unless you've sort of sorted the array beforehand to get the optimal pivot, sometimes you pick a bad pivot. And the thing that we like to do in algorithms class when we're talking about quicksort is we talk about randomized quicksort, where if you just pick a random element from the array, sometimes it'll be bad, sometimes it will be good, and on average it's the same as if it were always good asymptotically to sometimes get a bad pick. But if we want to do this for a good parallel speedup, we want to avoid getting bad picks, because bad picks mean that some process gets starved in the number of items that it's going to be sorting once we start sorting the partitioned range. And the solution that we can use is we're going to just sort the array beforehand to get all the best pivots. Now, if we sort the entire array, then that's as slow as doing a sequential sort and we don't win anything. So instead of looking at the whole array, we're going to look at a representative sample of the data in the array. And this is making the assumption that the array isn't sort of maliciously crafted with data that's going to be hard to sample, and if we sample it, we'll tend to get bad pivots. That is actually possible. We could have an array that's quadratically distributed, where small numbers are significantly more common than large numbers, but the large numbers sort of stretch into a long tail. So if we start sampling and picking out random numbers, we're likely to get a biased sample. But assuming that we are able to sort of sample enough to get a reasonable idea of the contents of the thing, and things are evenly distributed enough that sampling works, we can take, assuming that we have a large enough data set, looking at a random like 1% of the input is going to be plenty. If we like take 1% of the input randomly, sort that 1% of the input, and then take out the optimal pivots. And when I say the optimal pivots, I mean, let's take a look at this input here. So if we wanted to split this into one group, the optimal pivot is 9, because that gives us 2 groups of equal size. But if we wanted to split this into 4 groups, then the optimal pivots are 3, 9, and 35. Because that'll split it into 4 equally sized groups of size 1. And so if we had 100 items in our input set, and we wanted to split it into if we wanted to split it into 10 equally sized groups, we would want to find 9 pivots, which, if the numbers range from like 0 to 100, the 9 pivots that we want, assuming that they're arranged evenly, are going to be 10, 20, 30, 40, 50, 60, 70, 80, 90. So then we have sort of conceptually evenly distributed numbers between them, if that makes sense. So that's what we're doing with sample sort, is we have this process where we are going to take an array of n items and some number p, the number of processors. The goal is going to be to sort the input array. And the steps that we're going to do are, first we're going to sample. So we're going to randomly select some subset of the items in the array. If we want to do this efficiently, we take like 1% or something. Or for the homework, we're just going to take 3 times p minus 1. This is going to end up being a bad sample, and you're going to get to see some of the results when you look at timings that'll show why we would have wanted to sample more. But this is what we're going to do. We're going to sample this many items from the array. We're going to sort our sample. We're then going to take the optimal pivots out of the sample, and then we're going to use those pivots for our partitioning. Then we'll be able to do our partitioning in parallel, so we get a effective parallel speed up on that initial sequential step, or the initial step that would be sequential in a naive parallel quicksort. And then once we've partitioned, there's actually no reason for a parallel algorithm anymore at all, because this is quicksort. So if we partition, and then we have each process sort its own partition of the data independently using like local quicksort from the library or something, then the resulting output is just the thing that we get if we stitch those arrays back together in order by process number. Right? There's no merging. If we partition and then we sort the partitions, the result is already in sorted order because it's quicksort. So that is the sort of motivation for what we're doing with sample sort. And we'll be doing this with processes in homework 6, and then you'll be doing it the week after with threads in homework 7. There's some slight different requirements for the assignments. For example, in this case, you're supposed to use mmap.io, whereas in the upcoming homework 7, you're supposed to use the read and write system calls for file I/O. Additionally, in both of these assignments, once you get the program working, you are supposed to measure the parallel speedup that you're getting. You'll be doing that on both your local machine with 1, 4, and 8 processes, and then once you get that working, you'll be doing it on the CCIS or Curry login server. But you want to make sure that you don't run anything on the shared Curry College server until you've successfully run your program locally and made sure that you don't just fork a ton of processes and break the machine. Because there's a bunch of students in the class who have to share this server, so we don't want to slow it down too much. Good runs here should run in well, the idea is that you're supposed to pick a big enough input that test runs take 10 seconds. You're supposed to do some like repeats so that you can take medians, I think. Yeah, repeat each test 3 times. So you're supposed to do 3 scenarios times 3 situations. So that's going to be 9 test runs. So you should be on the shared server for maybe 5 minutes. And that should give everybody enough time to use it, as long as we don't bog things down too much. All right, so that is the homework. Good luck on the homework, and I'll be back to talk a little bit more about threads and the difference between processes and threads.